Hello dear students, welcome to Pen and Paper Chemistry on YouTube. This is video number 12 on the topic chemical kinetics, and today we shall be talking about the collision theory in this particular video. Now before we get started, please make sure that you have the pen and notebook ready to take down notes for offline reference, the general rule of the thumb for attending videos on this channel. We studied earlier that there are two types of reactions involving ions. So for example, when you dissolve salt in water, right? That's a reaction which involves ions of sodium and chloride dissolving in water. The other we studied were the reactions involving molecules. So for example, when we dissolved sugar in water, I hope you remember the small experiment that we did on dissolving sugar and salt in water, right? Now, here we will notice that the reaction involving ions are usually fast, whereas those involving molecules are relatively slow. The reactions involving ions, what do they involve? They simply involve electrostatic forces of attraction between oppositely charged ions. Whereas in the case of molecules, you first need to break down a molecule so that it can interact with the second reactant molecule, right? Let's see the example of sodium chloride. Now, each sodium ion is surrounded by 6 chloride ion, and each chloride ion is in turn surrounded by 6 sodium ions, right? That is how it goes on. Now, when we dissolve it in water, by the way, the change that I'm talking about over here is a physical change, but it helps me to explain the concept to you very easily. Here I have got the molecule of water. We know that water is a polar molecule having a positive and a negative end. If the positive end of the water molecule approaches the positive sodium ions, do you think an interaction is possible? No way. They are going to repel each other. Positive is going to repel the positive. So, what strategy does water apply? Yes, it starts approaching the sodium from the negative end. So, what have we got over here is it involves the interaction between ions or the opposite ends of a polar molecule. So positive being approached by a negative. If, let us suppose, instead of a molecule, I have another ion, right? So for example, I am reacting an aqueous solution of sodium chloride with silver nitrate. So Ag positive, NO3 negative, sodium positive, chloride negative. So what does the reaction entail? It simply involves the exchange of ions. Sorry, 1 minute. Yes, by mistake I had written silver chloride instead of silver nitrate. So what happens over here is there is interaction between the oppositely charged ions, and sodium combines with the nitrate ions, this forming NaNO3. Silver ions, on the other hand, are approached by the chloride ions, and we have the molecule of silver chloride, right? So simply, in the case of ionic compounds, the reaction involves the exchange of ions, as you can notice here. But can the same be said about covalent molecules? So for example, I have H2 plus Cl2 giving me 2 HCl. Is it that easy in the case of covalent compounds? How and what decides the formation of products in the case of covalent molecules? In order to explain this, we have something which is called as the collision theory. So what does the collision theory state? This collision theory is actually based on the kinetic theory of gases, and it was given by Max Strotz and William Lewis. if you know the kinetic theory of gases, because that is what you've been studying since your grade 9, wherein we say that any substance, any form of matter is made up of molecules. The molecules are considered as hard spheres. The molecules are in a state of constant, random, rapid motion. So they are like this, all over the place, going around like this, right? And in the process, what will happen is these molecules, they collide with other molecules. So if let's suppose I have a molecule over here, then the molecules are going in a rapid random motion. So the two particles will collide with each other. Now, because of this collision, either they will pick up a fight or they will not pick up a fight. Correct? So, what is the technical term we say for that? By the way, I hope you are noting down these points because they will come in very handy when the mobile is not around and you don't have time to watch YouTube videos. So, if they pick up a fight, that means we have been effective. They don't pick up a fight, ineffective. What's the point of the two of them collide, right? For a collision to be effective, so when we say effective collision is one which results in the formation of products, right? An ineffective collision is one in which no products are formed. Got it? What is the criteria for a collision to be effective? First, the molecules must have the necessary threshold energy. Two people come across each other, they bang against each other, but both of them are very tired. It's like, oh, okay, it's okay, boss, fine, sorry, no problem. And they go their separate ways. They don't have the energy to fight. So, the molecules must have the necessary energy, what we call as the energy barrier. Now, do you remember in the previous video, we've already covered the concept of threshold energy, so I shall not be touching upon it in this particular video. For those who have not gone through that, it is very much there in the previous videos where we've talked about activation energy and threshold energy. The second is the molecules must collide in proper orientation, what we call as the orientation barrier. We shall be talking about this one in greater detail. Now, the rate of a reaction is dependent on the collision frequency. Now, wherever the word frequency comes in, that means the number of times they are colliding per unit time, right? Per unit volume in a given volume. And this collision frequency is given by the symbol Z and AB, or you can say ZAB. So this AB means the two molecules that I have got here. So molecule A and molecule B. So we've given them the names, the two molecules which are colliding, they are being called as A and B. You can call them as X, Y. So just for the, for the sake of clarity, we are naming them as A, B. So now if you remember in the Arrhenius equation, we had said K is equals to AE to the power minus EA by RT, which was the Arrhenius equation. From collision theory, we get the value of rate constant as ZAB e to the power minus EA by RT. So if you compare the two equations, now this derivation K is equals to ZAB e to the power minus EA by RT is by complex mathematical steps. We are not to go into the details of this at this point of time. So in other words, your A, the frequency factor, is the same as the collision theory according to the equations that we have here. So also known as the frequency factor. The next point that we see, only molecules with the necessary energy will be able to collide effectively. Oh, my spelling of effectively. Yes, there's a C over there. And very logical. Lower the activation energy, faster the reaction. Now, what is the activation energy? The minimum energy the reactant molecules must acquire. So, let me just go through that graph again, right? This was our energy of the reactants. This is not an exact graph. This is just a recall of what we've done earlier. This is the energy of the products. Now, your reactants, they, in order to be able to form the products, they have to go all the way up the hill and come down the hill. Now, what is this uphill and downhill? This is the energy barrier. That means in order to be able to form the products, first they must acquire this much amount of energy, what we call as the threshold energy. Threshold is like the borderline of your house. In order to be considered outside the house, you have to cross that threshold. You are inside the house when you just step in that border, right? So this is, here you are, this is your house, and this is the door of your house. So this is your threshold. You keep your feet inside it, you are inside the threshold. You cross this line and you are outside the threshold. So they must clear this threshold. So the minimum energy that the reactant molecules must acquire in order to reach this threshold energy is what we call as the activation energy. In other words, if let's suppose I have a reaction whose threshold energy is this, you see ET over here. Which of the two reactions, the one in black or the one in blue, will take place faster? Yes, of course, the one in blue. Why? Because the threshold energy is lower. The reactant molecules have to acquire only very small amount of energy in order to reach or in order to cross that energy barrier. Oh, I ended up explaining the concept of activation and threshold energy again. So now that we have spoken about the activation energy, we are going to explain what do you mean by effective collision and what decides that efficacy of the collision other than the activation energy. And that factor is what we call as the orientation factor. Now, in order to explain the orientation factor, I took up an example of a small kids game. Let's watch this video in order to understand. Okay, let's play a game, which I used to play with my kids. It's called the game of dashing cars. So this car will come and it will dash against these two cars. Now, let us see in which, what is the orientation of this car and how it will affect both the cars which we are talking about, the yellow and the silver one. Okay, let's see. So this goes and, oh my God, did you look at that? You see, the yellow car collided with the green car, whereas the gray car remained unaffected. So that means the orientation of this car was apt to hit the yellow car, whereas not to disturb the gray car. And this is what we mean by the correct orientation when it comes to effective collision. Now, if you notice carefully, see, this blue car, it did come against the silver car a bit, yeah, but it has not done any damage. In other words, the collision was there between the green car and the gray car. But what happened? That collision was not effective. Whereas it hit the yellow car, and when it hit the yellow car, it banged and it went back. That means the collision with the yellow car was effective, whereas the collision with the gray car was ineffective. So I hope this video helps to make the concept of effective collision, ineffective collision, and the most important orientation factor clear to you. But you must be wondering, how do we apply it to molecules? For that, I'm taking a very simple example of the reaction of carbon monoxide with oxygen. So carbon monoxide burns with a blue flame in oxygen to form carbon dioxide. Now, let's see what happens here. Carbon monoxide molecule and oxygen. So I have drawn it as oval shapes over here, longitude, so that I can show the approach. Now, oxygen is an electronegative atom. So what is happening over here is the oxygen has a slight negative end, whereas here also, if it is approaching the oxygen is approaching each other, what will happen? Are they going to like each other's presence? No way. So oxygen tries to be smart, and it tries to form an alternate route. So what this oxygen does is, he says, instead of approaching it from the front, let me try and make friends with the carbon. So the oxygen molecule actually approaches from the carbon end, and carbon immediately develops a liking for the oxygen and is very happy. And that gives me a product, that is carbon dioxide. In other words, this collision was effective, whereas this collision was ineffective, right? So what has happened here? What did we change? Our reactants are the same, our activation energy is the same. What has changed is the orientation, how it is being approached. The orientation has changed of the two reactant molecules. So we need to account for the orientation factor in our equation. K is equals to ZAB e to the power minus EA by RT, because this equation, yes, talks about the collision frequency. It takes into account the activation energy, but it does not mention the orientation factor at all. So what do? We introduce a correction factor, which is the orientation factor represented by P, ZAB e to the power minus EA by RT. This P is our orientation factor, or it is also called as the steric factor. Now this orientation factor or steric factor is going to be very, very useful when you study the organic compounds. So if you have an idea about organic chemistry, so I've got an alkyl halide over here, and specifically let me take a primary alkyl halide. Now here, halogen atom, it acquires a partial negative charge because of its high electronegativity. So do you think if OH, the nucleophile, if it approaches from this end, will it be effective in forming a product? No way. Bromide is going to shut the door to OH negative and say, come on man, move away from here. This is my area. You better not mess around with me. So again, OH, what does it have to do? Yes, it finds a via route. Says, okay, let me try and go and make friends with carbon. instead of approaching from the front. That means it's more of a backdoor entry approach that OH negative, the nucleophile, applies. So here we have, you see now, Br is also connected to carbon and OH is also connected to carbon, whereas my 3 hydrogen are there and very much intact. See how smart and cunning this OH was. It managed to find its route inside the molecule by orienting itself properly. Now, what does this lesson teach you about chemistry? Yes, I am not talking about the collision theory. Here, it simply means that you have to study. That means you have to collide with your books, but that collision has to happen with some minimum energy. That means you should have interest in the subject. You cannot say, oh, just because I have to do it, I will do it. If you show some minimum interest, you will start liking the subject. And the most important thing is proper orientation. That means proper approach to the topic, proper approach, how to study a topic. How have we been doing on this channel? We are breaking down each and every topic into small parts so that it becomes easy and fun for you to understand. Enough of Gyan for today. Stay safe, stay happy, stay healthy. The topic doesn't get over. We yet have to talk about molecularity, about which I forgot completely. So we will still be covering molecularity in the next video.